The question says which of the following complexes exhibits the highest paramagnetic behavior. Always keep in mind paramagnetic behavior depends on the number of unpaired electrons. Higher the number of unpaired electrons, higher is the paramagnetic behavior. Whenever the question is related to hybridization, geometry or magnetic properties, apply valence bond theory. To apply valence bond theory, we follow the orders. We have first write oxidation number of the central metal atom. Next we write electronic configuration of central metal ion. Next we have orbital notation. Orbital, we have orbital notation. And in orbital notation, before filling electrons, we consider the effect of ligand. If we have strong field ligand or weak field ligand. Strong field ligand either causes pairing of electron, weak field ligand no pairing of electron. Okay, no pairing of electron. Now this question is quite a special question. Why? Because there are some complexes in which more than one types of ligands are given there. In this case, only one type of ligand. Okay, but in this complex, you can see more than two different types of ligand. Here also different types of ligand. Here also different types of ligand. In this case, how we can apply valence bond theory? Very interesting part. First of all, I come to first complex. In this case, you can see ammonia. In general, we have learned, any ligand starting from carbon or nitrogen acts as a strong field ligand. But in case of ammonia, you should be careful, because ammonia obviously it acts as a strong field ligand, but it does not act a strong field ligand with all the metals. It acts as a strong field ligand only with selective metals, and those metals are, we have cobalt, cadmium, copper and iron is there. Only with these metals ammonia acts as a strong field ligand, and with remaining metals it acts as a weak field ligand. Hence we can say ammonia is acting as a weak field ligand in this complex. Means no pairing of electron. Okay, now we apply the steps to find out the number of unpaired electrons in this complex. Okay, the first we calculate the oxidation number of the central metal atom. We have, this is titanium is there, Ti is there, Ti. Okay, and plus ammonia is a neutral ligand, 6 molecules are there multiplied by 0, and total charge is what, plus 3 is there. Then Ti is equal to plus 3, it is present in plus 3 oxidation numbers. Okay, next we have to write electronic configuration of central metal ion. Okay, Ti atomic number is what, 22. Right, electronic configuration we have 3d2 and 4s2 is there. Now it is losing how many electrons? 3, because it has plus 3 charge. Then we get 3d1 is there. Keep in mind, if d orbital is having unpaired electron, doesn't matter strong field ligand is there or weak field ligand, paramagnetic character will be there and will be there. Okay, odd number of electron, complete pairing of electron will not be taking place. Some paramagnetic character is there. Okay, if we go for the orbital notation, we have Ti plus 3 is there. In this case, d orbital, it is having only one electron, 3d, and in this case we have 4s is there. And anyway, we are not going to find out the hybridization, this step is not required. We fill this electron, one electron is filled. Ammonia acting as a weak field ligand. Okay, there is no pairing of electron, only one electron is there. Paramagnetic character is there because it has one unpaired electron, it has only one unpaired electron is there. Okay, one unpaired electrons. Okay, now interesting part, we move on to the next complex. You can see in the next complex different types of ligands are given here. This is what ethylene diamine, this is bipyridine, and this is what ammonia attached to the central metal atom. What kind of central metal atom? Iron will be acting as a strong field ligand. Here we have the strong field ligand. And one more thing, interesting part, this is what ethylene diamine, ethylene diamine, this is a neutral didentate ligand. In general, this is considered as a polydentate ligand. Polydentate ligands in general are considered as a chelating ligand. Chelating ligands form close ring with the central metal atom, and they increase the stability of the complex. Okay, a strong field ligand also increase the stability of the complex. Means chelating ligands will be behaving as a strong field ligand, hence pairing of electron will be taking place. Very interesting part. And if you do not consider the effect of ligands, you can see this, so many different types of ligands are there, and because of this you can see too much splitting will be there. When splitting is very high, in this case pairing of electron will be taking place. Keep in mind, strong field ligand also causes splitting. More splitting is there. Weak field ligand causes less splitting, that's why no pairing of electron. In a strong field ligand, more splitting is there, pairing of electron is there, and hence stability of the system increases because more amount of energy is released. Very interesting part. So you can see this is what a chelating ligand, and this is ammonia obviously acting as a strong field ligand, and pairing of electron will be taking place. Now we apply these steps to calculate the number of unpaired electrons in this complex. Okay, need some more space. We have Fe. Okay, we have Fe. Calculate oxidation number. First of all, Fe plus ethylene diamine, it is a neutral ligand, it has zero charge. And then next, bipyridine, it is also neutral ligands. Ammonia, it is also neutral ligands, multiplied by 0. Overall charge is what? +2. Iron is present in +2 oxidation numbers. Okay, next we write oxidation, electronic configuration. Next we write electronic configuration. Keep in mind, Fe atomic number is what? 26. It is 3d6, 4s2 is there. For Fe2 plus, we have to write electronic configuration. It will be 3d6 because it is losing 2 electrons. Now we go for the orbital notation. We have Fe2 plus is there. In this case, 3d6 is there. 3d6 is there. And then we have 4s vacant orbital. Then we have 4p is also vacant orbital is there. Keep in mind, in this complex, we have ethylene diamine as well as ammonia acting as a strong field ligand. Okay. So stability of the system is increasing, means will be causing pairing of electrons. Now we start pairing of electron. When pairing of electron is taking place, keep in mind diamagnetic character increases and paramagnetic character decreases. In this case, you can see we do not have any unpaired electrons, 0 unpaired electrons. It does not have any paramagnetic character. It is diamagnetic by nature. Okay, so it does not have any unpaired electrons. I can mention it is 0. Okay, now move on to the next complex. In this case, okay, cobalt is there. Okay, this is OX. This is what oxalate ion, and oxalate ion is also considered as a chelating ligand because it can form the closed ring with the central metal atom. Okay, because it can also form the closed ring with the central metal atom, and hence it will be increasing the stability of the complexes. Then it will also behave as a strong field ligand. But anyway, you can see this is what didentate ligands, didentate negative ligand, and this is what unidentate is there. They will be causing more splitting. Hence, will be acting as a strong field ligand, will be causing more stability to the complex. Then leading to the pairing of electron. Conclusion is what? Leading to the pairing of electron. Here also pairing of electron will be taking place. And hence, when pairing of electron is taking place, means diamagnetic character will increase and paramagnetic character will go down. Okay, let's calculate the oxidation number. Anyway, we have oral minus charges. We have cobalt is there, and OX whole twice, OH whole twice, and oral charge is what? Negative. Okay, cobalt plus OX. Each oxalate ion carrying -2 charge. It is a didentate negative ligand. Didentate, it has -2 charge. 2 multiplied by -2 is there, and plus 2 bracket -1 is there, and overall charge is what? -1. Cobalt -4 -2 is equal to -1. Cobalt is equal to -1 plus 6 is equal to +5. Cobalt is present in +5 oxidation numbers. Okay. Next, following the steps under valence bond theory, we write electronic configuration. Okay. Next, we have electronic configuration. Cobalt atomic number is what? 27. Electronic configuration, outermost electronic configuration is 3d7 4s2 is there. 3d7 4s2. Now, cobalt having +5 oxidation number, +5, losing 5 electrons, 2 electrons from here and 3 electrons from here, then it will be 3d4 is there. And now keep in mind, we are going to write the orbital notation, in which when we fill the electrons, pairing of electron will be taking place because oxalate ion is there. It is a polydentate and chelating ligands. Okay, we have cobalt +5 is there, and we have 3d4 is there, 4s is there, and 4p is also there, 4p. In this case, you can see 4 electrons are there, 1 2 pairing of electron, and pairing of electron is there, so diamagnetic character is increasing, and paramagnetic, because it does not have, you can see it does not have any single unpaired electron. In this third complex also, we do not get any unpaired electrons. It has 0 unpaired electrons. Now last, vanadium is there. This is glycine. Okay, this is glycine is there. It is a neutral ligand. Okay, OH is there, and ammonia is there. Ammonia, you can see 3 different types of ligands are there, and it is acting as a didentate ligands. Didentate ligands you can also consider as a chelating ligands. Hence, it will be causing more splitting and leading to the stability and leading to the pairing of electron. okay, leading to the pairing of electron. Hence diamagnetic character will increase and paramagnetic character will decrease. Okay, so in this case also ammonia, anyway you can see ammonia attached to cobalt, cadmium, copper and iron will be acting as a strong field ligand, with remaining metals will be acting as a weak field ligand. But anyway we have didentate ligand is there. Okay, means pairing of electron. We calculate the oxidation number. You can see this is neutral ligands, 0 will be there. This is OH minus negative unidentate ligands, minus 2 is there. Overall charge is what? Plus 1 is there. Vanadium minus 2 is equal to plus 1. Vanadium is equal to what? Plus 3 is there. So we got plus 3 charge. Okay, plus 3 charge is there. Now we apply valence bond theory to calculate the number of electron. We got vanadium having plus 3 charge. We have vanadium having plus 3 charge. Okay, so we write electronic configuration of vanadium, scandium, titanium and vanadium. Its atomic number is what? 23. Then we write electronic configuration 3d3 and 4s2 is there. Okay, vanadium is having plus 3 charge, and for this we have to write outermost electronic configuration. Losing 3 electron, then it is what? 3d2 is there, through 3 electrons lost. Now you can see even number of electrons are there. Pairing of electron will be taking place when we go for the orbital notation. You can see in this case, if we go for the orbital notation, vanadium it is what? Plus 3. It is 3d2, it is 4s, it is not required. 4p also not required. Okay, but anyway we write. Okay, 2 electrons are there, and there we have chelating ligands. Thereafter here we have pairing of electron. It also does not carry, you can see, unpaired electron. Unpaired electrons, it does not also carry unpaired electrons. Okay, here we have the question. In this case, in the D option also we are not getting any unpaired electrons. You can see this is diamagnetic, and we have only single unpaired electron in option A, and it is paramagnetic. It is not highly paramagnetic, but among these complexes we can say this is highly paramagnetic. Okay, these are, because remaining they are what? Diamagnetic by nature. They do not have any paramagnetic character. It has a paramagnetic character. Option A is correct. If you like this video, please share and subscribe to the channel.